All right, welcome everyone. Good morning. I'm Michael Holroyd. I'm one of the co-organizers of the conference, and I'm happy to introduce Sihang Jiang, who's a PhD candidate at University of Virginia's System Engineering. He's going to tell us about the research projects by the UVA iThrive organization on the National COVID Cohort Collaboration project. Thank you.
Uh, Hello, everyone. Hello, everyone. Just to make sure everyone can hear me clearly. And first of all, a little bit introduction of myself. So this is me. I'm a PhD student in systems engineering at University of Virginia, pretty close. Uh, and my research interests include Bayesian machine learning, Markov model, and AI for health. So this talk today is basically based on all of the research projects during my PhD journey. So I hope I can successfully defend my PhD sometime, maybe in the near future, right? It's a really long journey. So okay, let's start. This is the overview of my talk today. So basically two parts. The first section is an introduction about large multimodal data. And the second part is Bayesian risk analysis and how it could be applied to large multimodal data and what it can do in various projects. So, what is large multimodal data? Uh, Large multimodal data refers to vast and complex data sets integrate multiple types of information from various sources such as text, images, audio, video, structured numerical data, and sensor readings. And multimodal data is essential in the era of AI and large language model because it allows for the integration of diverse information sources. And this is how multimodal data could play a part in the COVID pandemic era and even in the post-pandemic era. So COVID pandemic catalyzed a rapid and unprecedented expansion in the generation and integration of large-scale multimodal data in different countries and regions in the world. And single modality data often cannot capture the full picture in complex domains such as healthcare. So we need large multimodal data to integrate more information and build more complex models and answer more research questions. So this is a figure of illustration how multimodal data could be worked for COVID-19. So there are several sources, as you can see in the picture, such as a lab test, imaging, pathology, symptoms, other clinical data, omics, and physiology data. I'm sure everyone here, if you try to think of the year of 2020, maybe you are during several months in the year of 2020, you are doing the COVID-19 test maybe every day or twice a week. So that is a particular type of the multimodal data, which includes various information, includes abundant information for pathology and symptoms and how the COVID-19 could be transmission dynamics of COVID-19. They are all included in that kind of info, that kind of data. And this is another example or illustration how a multimodal framework versus unimodal framework. So basically, a multimodal AI model could include text, image, and video as input, and you train an AI model on this very complex and multimodal data from various sources. You can get a wide range of results, maybe on some very complex problems. And for the unimodal AI model, it only has one specific type of data for the input. As you can see here, this is in this picture, the unimodal AI model only takes a picture or images as an input. And this is another picture of how multimodal data could play a part in healthcare. So we have various types of data. I just listed a couple in the picture. And if you apply this data to the artificial intelligence or machine learning models, it can help with different tasks, such as disease detection and screening, disease diagnosis and treatment response, or even drug development. So this is how multimodal data could play a part in the healthcare. And that's basically the theme of my talk today, because my advisor has an appointment for the integrated ISRAP, which is a healthcare. It's based on School of Data Science at University of Virginia. I will talk about it a bit later. So here are several multimodal databases, as you can see, all over the world, not only the US. Many of them are developed during the COVID-19 pandemic, or they existed before the COVID pandemic, but they developed a lot during 2020 till now. So first one, European Health Data and Evidence Network. This is a database for European Union. And UK Biobank and Open Safely. They are the databases from UK. And National Pandemic Cohort Network in Germany. And Population Health Research Network in Australia. And National Database of Japan. The name is just too long, but includes similar info as all of the other datasets. It includes the healthcare information, for example, the insurance claim data for all kinds of various diseases, and the electronic health record data for COVID-19 patients and many other patients as well. That's the databases from other countries, but that's not related to my work. I just refer it as reference because my work mainly focused on the data in the US and some of the data in the VA state. These are the two databases I mainly focused on during the past 3 or 4 years. The first one is N3C, National COVID Cohort Collaborative. This is a project or a database started by NIH. And at the starting point, it collects electronic health record data only related to COVID. For example, how many patients are tested positive for COVID, and what are their vital measurements data from hospitals, such as blood pressure, oxygen saturation, and whether this patient has an inpatient visit or outpatient visit, and what's their drug prescription. So that's the format of the data in this N3C large database. And ISRIVE is, the full name is Integrated Translational Health Research Institute of Virginia. Well, that name is also too long. I can never remember that. Well, this is a research institute initiated by several institutes, including UVA and VTech. So the aim of this research institute is to kind of replicate the methodology from N3C, and it's also sponsored by NIH. But ISRIVE mainly focused on the data in VA state. So we have several data partners that provides this patient data, including UVA Health. And there are also several projects going on studying the healthcare, what's going on in the VA state. So this is the front page of N3C, National COVID Cohort Collaborative. This is a website of N3C. So if you are interested, you can just Google the three characters, N3C. N3C, you can Google that if you are interested. So it has more than 9 million COVID positive patients there, and more than 22 million patients in total. So not really limited to COVID positive only. And there are more than 33 billion rows of data. As all of the 33 billion rows, they are electronic health record data. As I mentioned, it includes drug exposure, clinical visits, and vital measurements, and so on. So all of this data, they are contributed from more than 90 contributing sites, and these sites including universities and hospitals all over the US. There are already over 500 projects going on in this large database because we have such a large data set. So if you're interested in anything, you just grab the data and do some data analysis. It cannot be successful without the cooperation of many different universities and researchers. But as you all know, what's happening in 2025, so some of the projects are terminated because of the unforeseen reasons. But this data platform is still there, and I believe it's a very powerful platform where you could do the online computing, cloud computing, and do the projects. They're all stored in the cloud computing environment. So yeah, these are the examples of multimodal data sets in N3C. Well, there are several things I might not have mentioned yet. So there are also zip code and FIPS code info from US Census, also stored in N3C. And social vulnerable index from CDC, they're also stored in N3C. Yeah, so there are healthcare data, but some of them are also socioeconomic data. Most of the time, they are correlated. And this is iThrive, Integrated Translational Health Research Institute of Virginia. So it's also a collaborative clinical and translational research institute. So it partners with Carolyn Clinic, UVA, and VT. And it provides us, it sustains inclusive clinical and translational research to improve human health and promote health equity, mainly in the state of VA, because the data are all from the state of VA. Well, this is how iThrive utilizes the research data. So it also has a cloud computing environment. It's called Research Data Commons. It is a single interface to manage, share, and use research data, quite similar to N3C, but on a different cloud computing platform. So this is also a multimodal database, mainly focused on data from Virginia, as I mentioned. That's pretty much of the databases I want to introduce. And the N3C and iThrive are the two databases that I mainly focus on during the research, during my PhD journey. And the method I mainly applied is called Bayesian risk analysis. Just to make sure everyone knows Bayesian risk analysis, it is a framework for decision making under Bayes' theorem. I know this is a data science conference, so I guess most of you, or maybe some of you at least, know Bayes' theorem. It's the ultimate rule for a Bayesian person in comparison to those frequentist methods and researchers. So this is the ultimate Bayes rule in Bayesian inference. Very classic and very simple. So it basically tells us the posterior of a parameter theta, it is proportional to the prior distribution times the likelihood. And the likelihood is from the data you observed. So basically, it means that the posterior estimation of a parameter, it can be in a very complex model. The posterior estimation has combined the info from your prior belief on this parameter and the evidence you observed from the dataset. Bayesian methods model, it models the uncertainty by treating parameters as random variables, allowing for continuous belief updates. I think this is the core difference that Bayesian methods have, different from the frequentist methods. It treats the parameters as random variables, and so the random variables have a distribution. And this might be too mathematical here, but only one page. So this is an example of the predictive distribution. Predictive means you care about prediction. You train a model when you have new observations. You want to know the response variable, what it is like. So just give a simple example for linear regression. You observe several data and you train a linear regression model, try to find a linear relationship between y and x. Now you estimated the coefficients beta hat, and now you have a new data point, x star, and you want to know the distribution of y star, right? So in the frequentist approach, you just plug in the value of x star, and you'll get a point estimation of the y star. But in a Bayesian approach, you need to integrate out the parameter, the distribution of parameter theta, because theta is a random variable here. It has uncertainty. So the prediction of y star becomes also a distribution. Yeah, I try to illustrate this in an example for the predictive distribution. That goes a little bit theoretical, but we'll be back to some applications in the real world. Mainly three contributions from my projects. The first one is about the transmission dynamics of COVID-19, and of course it's in the year 2020 and 2021. Because the CDC has declared the end of federal emergency of COVID-19 pandemic, so people are not really interested in the transmission in this year. But people are still interested in the characteristics of long COVID. Long COVID is a new disease defined by the CDC. It is a long-term result of the COVID pandemic. And people are also interested in the healthcare equity in different groups because many research groups have observed that underrepresented groups in the US, they suffer from healthcare inequality, and they cannot have as good healthcare as other people should have. So about the COVID transmission dynamics, compartment model in epidemiology is very commonly used. To explain it in a plain language, suppose everyone in Charlottesville could possibly be infected by COVID-19. We can divide the whole population living in Charlottesville into several states. These are a classical model in compartmental models. So we just divide everyone living in Charlottesville to 3 or 4 states. S here represents susceptible, E represents exposed, I means infected, and R means recovered. And on the population level, everyone could be transferred from this state to another state and back and forth. So it's a dynamic system here. So SIR and SEIR model are classic compartmental models, and my work added a little bit stuff. I focused on the transmission dynamics via wastewater because of the viral characteristics of COVID. So the viral load in the wastewater could be a sign of how COVID transmission rate is like. Well, because in a region with insufficient testing, the confirmed cases of COVID might be misleading. So if people are not going to test for COVID, then we're never going to know the real number of cases. So this is a novel version of SEIR model in my work. So as you can see here, S, E, and I, and R, they still represent the classic states in a COVID transmission dynamics. I added another state, RS, meaning that some COVID patients, they are already recovered from the disease, but they are still shedding viral load into the wastewater. And the V and C here represents the viral load in wastewater and the reported confirmed COVID cases in a city. So the notation on the plot here represents the parameters representing how the transmission rate from one state to another. And my work and how Bayesian risk analysis play a part is to estimate these parameters, maybe 1, 2, 3. And the data source we used is right here. It's the COVID viral load in the wastewater treatment facility of New Haven, Connecticut from March 2020 to May 2020. The resource data, the data includes confirmed cases every day in New Haven, Connecticut, and the viral load every day in Connecticut, New Haven as well. So this is a hidden Markov model because what we can observe only includes the confirmed cases every day. And also you can test the viral load in the wastewater, but you cannot observe how many people in a city they are exposed to COVID and how many people are already infected. You can only know the infected people by testing, but only a part of the population will go to test themselves. And hidden Markov model is here. It's applied to estimate the parameters. So only V and C are observed states, and all of the other states are hidden. And the result is here. So my research group, we had a paper in a conference, and if you're really interested, you can try to Google this paper title. There are details of what the parameters look like. This is the first contribution of myself, I guess. And next, I want to talk a little bit about the characteristics of long COVID. So by the CDC, the Federal COVID-19 Public Health Emergency Declaration ended on May 11, 2023. But the long-term effects of COVID-19 pandemic are still affecting everyone's lives. So long COVID is defined as a chronic condition that occurs after this viral infection and present at least for 3 months. And the ICD-10 code database is a code database to diagnose specific diseases, and there's a code called U09.9. This is a code to identify long COVID patients. It's also issued or first started by CDC. Existing research papers, they have investigated the risk factors of long COVID, which means what kind of patients they are more likely to get long COVID. But limited research has focused on the mortality risk of long COVID among COVID positive patients. So in my project, I want to learn more about what's the survival trend difference for long COVID patients and COVID positive control patients. Is there any survival probability difference, or is there any survival length difference? And this is the data I used for this project. As a result, there are like 47,000 long COVID patients and 47 COVID positive control patients. They're all from N3C. And why is it a 1-to-1 ratio? Because I did a matching to get every long COVID patients a control patient. Because of long COVID patients, they only take about 2% in the bigger COVID positive patients. So if you're going to train a model in this imbalanced data, you'll never get a good result. I'm pretty sure data scientists always face this problem. So when you do a classification problem, there are like 99% of zeros and 1% ones. It's not a good data set. So you need to do some resampling. It's good that N3C have many patients, so that even after this one-on-one matching, I can still have several thousand long COVID patients and COVID positive control patients. No, 47,000 actually. So what I did was use the Bayesian generalized linear regression model using a log normal distribution to describe the survival length, because survival length is always positive from day 0. And the detailed definition of day 0 of survival you can also find in some paper I will show in the next page. But the only thing I think I should stress is that it's a Bayesian version linear regression model to describe the survival length. And the Markov chain Monte Carlo methods are applied to estimate the parameters. So this is a visualization of the difference in the two groups of patients. As you can see, long COVID patients, as time goes by, long COVID patients have smaller probability of survival. It's maybe not that significant, but it's already distinguishable. So this is another preprint of my work, and I'm still actively submitting it to some journals or conferences. Okay, so last topic, COVID healthcare inequality. So, investigating the health inequality reviews how underserved population experience barriers in access to COVID-related care, helping to pinpoint systematic gaps in the healthcare system. It also helps the interventions and public health strategies that promote fairness and improve outcomes for vulnerable communities in future health crises. Before I dive into the data, I want to talk a little bit about Bayesian hierarchical model. Bayesian hierarchical model is particularly useful when you have group level data. So as you can see, there are three ways of doing a Bayesian model. In part A, you just treat every observation as the same parameter setup. They're from the same group. For example, if a patient from Maryland is different from a patient in Virginia, and you just ignore this difference, you could just treat them as the same from a parameter level. And the third one is independent analysis, meaning that we have a separate model for all patients in Virginia and a separate model for all patients from Maryland. And they don't share any information. They don't share any common information in the parameter setup. And the second model here, the hierarchical model, is somewhere in between. So we believe that a patient in Virginia and a patient in Maryland, they share a little bit similarity, but they have their own parameter setup. As you can see, we can incorporate the common things behind the parameters by giving the parameters a hyperprior, and they share a common distribution. So this might be a little bit too theoretical, and I'll just stop here. The only thing I want to make clear is that Bayesian hierarchical model, it could be perfectly used in group level data when you have observations, data from different groups. So this is the data I applied about 800,000 patients with COVID-associated emergency department visits from 54 sites in N3C. And that's why I used hierarchical model, because the patients are from 54 different sites. They're in the whole US from different universities or hospitals. And just to give a brief result, patients in underrepresented race and ethnicity groups are less likely to be hospitalized after COVID-associated ED visits. So I think this is a very interesting result. So even everyone in this cohort, they have ED visits. They all visited emergency department, meaning they have a little bit severe health conditions. The minority groups, they are less likely to be hospitalized. This is the paper on this project. It's already published in 2023, so I hope the ED visit situation is better now and in the near future. And this is a one-sentence summary. Bayesian risk analysis on large multimodal data is crucial for capturing uncertainty, integrating diverse data sources, providing quantitative evidence, and enabling personalized, equitable, and data-driven decision-making in healthcare field. And definitely, it's not only limited to healthcare field. Bayesian risk analysis could be applied to basically any field with complex data set. And special thanks to my PhD advisor, Professor Donald Brown, and colleagues of iThrive. Thank you.
We have time for maybe one quick question. Boom, first hand up.
Sure. Let's say you've got a long latent process that's not this process, and you're trying to figure out what features are important to collect. And what is your approach to feature importance ranking or feature extraction in characterizing your markup model when you only observe the outcome maybe months later or years later when the person died or didn't die?
That's a very great question. So if you're asking about feature importance, I think in a regression model or a linear all of the models, the linear structures, you can tell the importance from the coefficient, right? And you do the hypothesis testing, whether it's significantly different from 0. And for the tree-based models, such as XGBoost and random forest, you can calculate the feature importance by a special metric. But I think when a patient dies, so you mean there is latency between the feature importance and the observation, right?
Yeah, and you need to know what to collect, what data to collect, because the collection is expensive.
That's why we use this EHR electronic health record database. So basically, they collected every possible observation when a patient visits hospital. So basically, vital measurements such as blood pressure, oxygen saturation, and so on, and what drug exposure this patient has. Does this answer your question?
Well, let me jump in. I would encourage everyone to find Sihang afterwards for more questions while we rush on to the next speaker to keep us on track.
Okay,
Thank you again very much.